All right, guys, welcome to a special segment on ETA. This is where we bring you the best in maths and physics. But today I'm going to be focusing on physical sciences. And I'm going to be focusing on a special topic of waves. So I'm going to be doing physical sciences grade 10. So I'm going to be teaching about waves. Now, within the realm of waves, there's waves, sound, light, and electromagnetic waves, which we're going to talk about. So I'm not going to waste too much time. Let's get right into it. Waves. Okay. First thing to know about waves is that a wave consists of a pulse. What is a pulse? What is a pulse? A pulse is a single disturbance. Okay, let's say we have a wave. Let me draw a wave on a Cartesian plane. A wave is a to and fro movement. So this segment segment here is what we call a pulse. And the entire thing is a wave. This is one wave. This is one wave. And if I put points A, B, C, D, our pulse is A, B, C. A, B, C. Okay? Now, what is a wave? A wave is made up of more than one pulse. So this is a wave. This is one wave because we had a to and fro movement. And the entire segment from point A to B is what we call a wavelength. Now, what is a wavelength? A wavelength is a distance between two consecutive points, two consecutive, you must know the word consecutive, two consecutive points. Two consecutive points that are in phase. Now, what do we mean by the term in phase? Now, the particles in a medium are in phase if they are vibrating perfectly. Points or let me say particles, are vibrating perfectly. In other words, if 2 points on a wave have the same y position, same y position, and same gradient. You won't find this definition in your textbook. It is my own definition, and it works. So, for an example, let's say we have 2 waves. Okay, so let me call this E. E, F, G, H. So H, let's say we have H, we have point I, and we also have Z, I, J, sorry, point J, these 2 points. If their values are the same, if their y values are the same, let's say for instance, if we are comparing I and J, if they have the same y value, do they have the same y values? Yes. If you draw a straight line, it is going to cut the same y value. But do they have the same, are they resting on the same slope? Let's see. The answer is yes. So I and J, so I and J are in phase. So what are other points that are in phase? Let's try A and C. A and C, are they in phase? No, they are not in phase. Why? Do they have the same position, or the y value or y position? Yes, they do, but they do not have the same slope. This slope is positive, and the slope at C is negative. Okay, let's try A and D. Are they in phase? The answer is yes, they are. If you draw the slope, they're gonna have the same slope. The same slope that you're gonna find at H. So A and D and H, they are in phase, all of them. A, D, and H are in phase. Okay, so now we know what the term in phase means. What we have on the screen is a so-called a transverse wave. We're gonna be dealing with 2 types of waves. We're gonna be dealing with transverse and longitudinal waves. Now, what is a transverse wave? A transverse wave as particles that vibrate at 90 degrees to the wave direction, to the wave direction. So let us go to the graph and see what we mean. So if you check this graph, you will see, let me change the color. If you check the graph, you will see that the direction of the wave is like that. Let's say, for instance, if you put a loose ball here, if you put a loose ball beside, if this wave is moving in this direction, when this wave comes, this ball will climb the wave, and when the wave passes, it will go down. So it will continuously do the same. So whenever the wave is moving, this particle will be going up and down, up and down, up and down. So that is why we call this wave a transverse wave. I hope you understand. Now, this wave has a wavelength, and an aptitude. Sorry, and an amplitude. Yes, an amplitude. So an amplitude is the distance from rest to the highest point which the particle will move, because your particle will be moving up and down. They will be making a to and fro movement. That is what a wave is. A wave is a to and fro movement. So it's a to and fro movement. So a wave, right? A wave, vibration or a vibration, or an oscillation is a to and fro movement of particles in a wave. In a wave. So I said something about an amplitude. Amplitude. I don't know why I keep on making mistakes. Amplitude. This is the maximum displacement. Displacement from the place of rest. From the position of rest. From the position of rest. Okay. We also have a term like frequency. Now, when a wave is moving, we need to count how many times that the wave has passed a specific point. So the number of wavelengths passing a specific point is called frequency. Passing a point on a wave. It's called a frequency. Okay. Now a frequency, the inverse of a frequency is called a period. Now what is a period? Frequency is denoted by F. That's frequency. Now period T is the time taken by one wavelength. To pass a point. Okay. Now, lastly, we have the term wave speed. Wave speed. Now, the wave speed is measured in meters per second. Of course, it is the distance moved per second by a wave, a wavelength. Okay. Now, there's certain terms that we have to bear in mind also. I have talked about a pulse. A pulse is divided into two segments. It's a crest. Let me put a nice representation. Okay, we have a pulse. A pulse comprises of a crest and a trough. A crest is a hump, and a trough is a sag. This is a sag. This is a hump. So on a wave, where is the crest of the wave? This is the crest. This is the crest. This is the crest of the wave. This is the crest. This is the trough. The trough. Okay. Now, what is the formula for the wave speed? The wave speed is given by distance over time. Distance over time. Now, if you separate the two, I don't know if you will agree with me. Okay. What you will have is 1 over time times distance over 1. That's what we have. Now, the units for period is seconds, and period is given by 1 over frequency. You must just cram those formulas if you have to. It is what it is. I have said it before. Your period is the inverse of frequency. Okay? So if period is the inverse of frequency, it means frequency is also the inverse of period. So f is given by 1 over t. So if you take the inverse, you will agree with me that we will have frequency times distance. And then what is the distance? The distance is the wavelength. So v equals frequency times lambda. And you must just know the formula by heart. And also v can also be given by lambda over t, since this is the inverse. Okay. These are the important formulas that you need to know. Okay, the other one is this one. You must know these formulas. Okay. We're gonna move to another segment of waves. Now, what happens when waves interact? When waves interact, there's some so-called superposition. Now, what is superposition of waves or of pulse? Superposition. Superposition. It is the addition. It is a vector addition of pulses when they collide. It's also called interference. Okay, there's two types of interference. If two waves that are in phase, if you look at them, they are in phase, the slope and everything. If you add the two waves, you're gonna get a larger amplitude. You're gonna get the amplitude will be the amplitude, yes, will be the sum of the two amplitudes. The amplitude of this wave, it will be if it's x, it will be x plus y. That will be the amplitude. And this is called constructive interference. Okay, so what happens when two waves are not in phase? Ish, my drawing skills. Okay, if they are not in phase like that, they will destroy each other. Let's say if these waves are the same, whenever they add, they will destroy each other, and the amplitude will be zero. This is called destructive interference. Okay, now we're done with the we're done with transverse waves. We are going to longitudinal waves. Now, longitudinal waves are an opposite of transverse wave, if you think about it, because the amplitude of longitudinal waves is actually the position, the distance from the rest position to the center of compression, to the center of compression, or rarefactions. Okay, I'm not gonna waste too much time. This is how a longitudinal wave looks like. A typical example of a longitudinal wave is a spring or a sound wave. The transverse waves, examples of transverse waves is it's actually transverse, it's actually light waves, and electromagnetic waves as well. So the distance from the rest position to the center of the compressions. Now this is how longitudinal waves looks like. They have okay. Now a section of concentrated lines is called a compression. This is how a sound wave moves. It moves in this way. It has compressions and rarefactions. These are rarefactions, and these are compressions, and these are also compressions. This is a rarefaction. A rarefaction is characterized by lines that are spaced. The same thing with a spring. A spring moves in this way. And the same thing with the sound. If you release a spring, it's going to move in this way and then comes back. Now, the amplitude, this is the amplitude. This is the amplitude. Now, longitudinal waves. With longitudinal waves, particle moves in the direction, because if you release a spring, all the particles are going to go in the direction of the wave. What we know is that with longitudinal waves, particles move in the same direction as the wave, unlike with transverse waves, because with transverse waves, particles move 90 degrees. I've already explained. Okay, and now let's talk about sound. Now with sound depends on the medium that it is moving in. Now sound always requires a medium to move, meaning it cannot travel in a vacuum or in an empty space. It cannot. And what we know is that sounds, the speed of sound is approximately 340 meters per second. And what we also know is that sound moves faster if moving in a dense medium, meaning it will travel faster if it's moving in a steel. Inside the steel, it will move faster than in water. And because water is denser than air, it will travel faster in water. So the 340 meters per second is the speed of sound traveling on air. I forgot to mention, traveling in air, it will have the speed of 340 meters per second. Now, we have two characteristics that I want to talk about. Characteristics of a wave: the frequency, frequency, and amplitude. Now, the frequency of the sound determines the pitch or the tone. So if the frequency increases, the tone increases. But the amplitude determines the volume of sound. So if the frequency of the sound increases, it means your sound will change from bass to a softer tone. For those who participate in music, what we know is that it will change from bass to soprano. But if you increase the amplitude of the wave, the volume increases. So you must take note, the volume increases. Now we are done with sound waves. Let's move to electromagnetic waves. So if that's number 3, this will be number 4. Electromagnetic waves. The name says it all. Electromagnetic waves. Now, this is a transverse wave. I don't have a good depiction, but an electromagnetic wave has got two transverse waves moving in the same direction but are 90 degrees to one another. So we have the magnetic field and let's say if we have the magnetic field and the electric field. Okay, the name says it all. Electromagnetic waves. Now, this is a transverse wave. Consisting of electric field or electric waves in a form of waves um, and magnetic waves moving at a speed of 3 times 10 to the power of 8 meters per second together 90 degrees to each other. Okay, now from what we know that the speed, this is the electromagnetic waves. Now the speed of a wave, which is given by C, in particular for an electromagnetic wave, is still given by the formula frequency times wavelength. Wavelength is depicted by lambda. Okay, now what we know is that because of the electromagnetic waves, we have the so-called the spectrum of the electromagnetic waves. So the spectrum, it is the arrangement of electromagnetic waves from higher frequency to lower frequencies. Higher frequencies are dangerous. They can damage a human skin, can damage a human being completely. But the lower frequency of electromagnetic waves are less harmful. So we have gamma rays, we have X-rays, we have UV rays, we have visible light, we have infrared, we have microwave, we have TV and radio waves. So TV and radio waves are less harmful waves. Okay, so why do we have to learn this? It is very important because we need to know which waves are dangerous. The most dangerous waves, of course, are gamma rays. Now, the gamma rays, let's talk about the gamma rays. Okay, the gamma rays are produced by radioactive materials. and have highest energy and have highest energy to can penetrate objects. Okay, we also have X-rays. They are used to produce a medical scan. They can also be dangerous, so you don't have to think that X-rays are less harmful than gamma rays. They are also dangerous. We also have UV radiation, which is harmful to our skin and eyes. Okay, we also have visible light. I won't talk much about visible light. We also have infrared, which is used in remotes. So it's the red light that you see on the remote. So that's infrared. And we also have microwaves. They are used in cell phones. Okay. Now we have the so-called the visible light. So I'm going to talk about the waves of light, or let me just talk about electromagnetic waves as a whole. Okay, what we know about them is that they have a wave nature and a particle nature. Now the wave nature we have already talked about. Now the particle nature we are going to talk about photons. The photons now the photons are particle of light. The particle of light, and they're carried by particles called quanta, or the quantum energy. So that's about it. I hope you have learned a lot out of this video. So I have tried to summarize everything within the waves and the wave sound and light. So if you have any question, you can go to the comment section, put your comment, and I will definitely answer you on a special segment. That's about it. Thanks for everyone who was part of this lesson, and cheers.